Hello students. So already we know about the Markovnikov and anti-Markovnikov addition of alkene. So in Markovnikov addition, we know if you take unsymmetrical double bond, then the negative part or nucleophile, it will attack to that carbon center of double bond where present less number of hydrogen atoms. Similarly, in case of anti-Markovnikov addition, if we use peroxide, then the whole process it will be reversed. That means nucleophile will attach at that carbon center of double bond where present more number of hydrogen atoms. So already we discussed about this matter in the previous class. So today we are going to discuss about some another additional reactions of double bond. For example, addition of sulfuric acid. Sulfuric acid, you know sulfuric acid is H2SO4, and if you find out the structure of sulfuric acid, then it looks like S double bond O, O my OH, and there is an OH, the structure of sulfuric acid. So in case of sulfuric acid, it will dissociate into H plus and HSO4 minus, and this HSO4 minus means from this molecule, this hydrogen and this hydrogen act as an acidic hydrogen, and it will remove from this sulfuric acid. Then it will form S double bond O, O minus, and if I say it is OH, then this is the actual structure of HSO4 minus. Now this molecule acts as a nucleophile for addition reactions. So if I take any unsymmetrical alkene means R, CH, double bond CH, it is unsymmetrical alkene, and if you use here H2SO4, then what will happen? First, it will dissociate into H plus and HSO4 minus, and you know the reaction goes to by electrophilic addition reaction. Then this double bond first attached with this H plus ion, and it will form a stable carbocation. Stable carbocation means R, CH bond CH3. Then only it will form a stable carbocation. That means a 2-degree carbocation. If this hydrogen atom will attach at that center, then the carbocation will form in this center, but it will form a primary carbocation which is unstable. That's why according to the electrophilic addition reaction, the carbocation, the most stable carbocation will form after addition of H plus. Then it is formed 2-degree carbocation. Then the nucleophile means HSO4 minus. HSO4 minus, this nucleophile will attach with this carbocation, and the product it will be R, CH, OSO3H. Why it is OSO3H? You can notice that this O minus in the previous structure of HSO4 minus, this O minus acts as a nucleophile. Then if I take this carbocation, then this negative charge will bind with this carbon atom. That means the actual product it is R, CH, OSO3H. That's why the final product it is OSO3H. So after addition of H2SO4, the product it will form OSO3H, and there is CH3. So this is the addition of sulfuric acid with unsymmetrical alkene. So if I write this equation once again, for example CH3, C, here present another CH3 molecule, double bond CH2, and if you add here H2SO4, then according to Markovnikov addition, the negative part means HSO4 minus, or you can say nucleophile, will attach to that carbon center where present less number of hydrogen atoms. That means that carbon center there present less number of hydrogen atoms. So the product it will be CH3, C, CH3, and there present OSO3H, and this one is CH3. So this is the overall reaction. Another example, if you take this type of example, for example this type of example, and if you take HSO4 minus H2SO4 again, then the product it will be the negative part, that means nucleophile will attach at that carbon center by present less number of hydrogen atoms, that is OSO3H, and one hydrogen will attach with this carbon. This is the product. So this is the addition of sulfuric acid. Again, for using by same mechanism, if you use water, you can say the addition of water, then the mechanism it will be same. So again, if I take this molecule RCH double bond CH2, and if you use here water and some amount of H plus as a catalyst, then it is called addition of water or water addition reactions to the double bond or to the alkene. Then the whole mechanism will be same with the previous one. So first double bond attached with this H plus ion, that means first the electrophilic addition mechanisms going on, and it will form a stable carbocation, that means positive and CH3. As it is 2-degree carbocation, then it is stable. Then this OH2, or it acts as a nucleophile, they represent 2 lone pair on oxygen atom. It acts as a lone pair and it will attach with this carbon center, and it will form RCH, CH3, and they present O, H and H, and one positive charge carried by oxygen atom, because this oxygen donate this lone pair or use this lone pair for formation of bond. That's why it carry positive charge. After that, this bond will break to neutralize this oxygen atom, and the final product it is RCH. They are present OH and CH3. This is the final product. So if we add water, acidic water, then OH it acts as a nucleophile, OH minus it acts as a nucleophile, and it will attach to that carbon center or present less number of hydrogen. So similar example, if we take this example again, if I take this example again, and if you use here H2O with some amount of acid, then just follow where present less number of hydrogen bond. If you notice that they present 0 hydrogen and they present 2 hydrogen, so they present less number of hydrogen. So the product it will be, they present OH and this one is CH3. So this is the product. So this is the addition of OH or addition of H2O to the double bond. Next one is addition of hypochlorous acid. Hypochlorous acid means HOCl. This molecule is called specially hypochlorous acid, and this hypochlorous acid will form by addition of chlorine with water. Then it will form hypochlorous acid. Normally in this hypochlorous acid, here chlorine it carry positive charge and OH it carry negative charge. That means the structure of HOCl, it is HOCl. It carry positive charge and it carry negative charge. That means you can say this OH part act as a nucleophile. So again, by applying Markovnikov rule, if we take unsymmetrical alkene, then negative part will attach with that carbon center by present less number of hydrogen. Again, if you use Markovnikov rule, then if you take ClOH, then this one is the negative part or act as a nucleophile, then the product it will be RCH. Here you can attach OH and there you can attach Cl. That means the negative portion will attach with that carbon center by present less number of hydrogen, and the positive portion will be attached with this carbon center, just like addition reaction. So this is the addition of HCl. Next, reactions of double bond, it is allylic substitution. Allylic substitution means halogenation at allylic position. So first you have to know about the allylic position. Which one is the allylic position? Normally the alpha position with respect to the double bond, it is the alpha position means the nearest position or the next position of the double bond, it is called alpha position. So you can say this one is the allylic position. So for allylic halogenation, you have to use some reagent which is called NBS or N-bromosuccinamide. You can use NBS or N-bromosuccinamide. So the structure of N-bromosuccinamide, it is this one is the structure of N-bromosuccinamide, and you have to use sunlight here because this reaction is a photochemical reaction, and by applying this reagent in presence of sunlight, the allylic bromination will take place. So bromine will attach at the allylic position. So this is the allylic bromination with respect to double bond. Normally this reaction goes to via radical mechanism. Radical mechanism means first it will form a stable radical, then the radical will attach with the bromine atom. So there are so many steps. So if I take this molecule, this is the allylic alkene, so they present one hydrogen atom. So what's happened, if we use NBS and sunlight, then in presence of sunlight, first it will form, in presence of sunlight, first NBS will form a bromine radical. So it is called initiation step. In presence of sunlight, it will form a bromine radical. Bromine radical. This bromine radical initiate the reactions and it will form a radical at allylic position. And you know the allylic radicals are the most stable radical. That's why first it will form a allylic radical. Then bromine minus again, bromine radical again attached with this radical, and after that it will form a allylic bromination product. So this is called allylic bromination of unsymmetrical alkene. But you have to remember that if we use NBS and sunlight, then always bromination occur at the allylic position. For example, if we take this type of example, so again if we use NBS and sunlight, then you have to remember there are two allylic positions. This one is the alpha position or allylic position. This one also the allylic position. Then any one of this carbon of this allylic position will be substituted by bromine. So the product, it will be bromine. You have to attach here. So this is the allylic bromination. Similarly, if you take this type of example, so they present a methyl group, and if you use here NBS and sunlight, then again see this is 3-degree position. So if radical will form at that center, then it will be formed 3-degree radical, and but if radical will form at that position, then it will form only 2-degree radical. Then you know 3-degree radical is more stable than 2-degree radical. Then the final product, it will be bromine will be attached here. So this is the final product of allylic bromination. Next one is ozonolysis reactions of double bond. Ozonolysis reaction. This reaction goes to via ozone, and in case of ozonolysis reactions, alkene react with ozone. Ozone, you know, that means O3 in presence of sunlight. So alkene react with ozone to form ozonides, and these ozonides are unstable and explosive compound. They are not isolated, but are further reduced with zinc and water. This ozonide will break down, and after that it will form a carbonyl compound. So the overall reaction, it is, if you take this molecule, for example R, CH, double bond CH, and R test, it is again unsymmetrical alkene. And if you use here ozone with sunlight, then ozonolysis reactions will going on, and first it will form a ozonide product. It is a 5-member cyclic transition state. So the ozonide, just the procedure is just break down these two bond and attach 3 oxygen atom here. That means R, CH, CH, and R test. And the ozonide looks like this. This is the ozonide product, just like a 5-member cyclic transition state. Always remember, first break down these 2 bond and try to write a 5-member cyclic transition state. So this compound is called ozonide product. And if you use here zinc and water, then it will rearrange to form a carbonyl compound, and during this rearrangement what will happen, this bond homolytically break down, and after that it will form this product RCH double bond O, and another one is R-CH double bond O, and the side product it is H2O2, the side product. So this is the final ozone lysis product. That means a carbonyl compound will form after ozone lysis. So if you notice that the final product, what is the final product? If you use first ozone and then zinc and water, then the final product it will be RCHO and R-CHO. So the shortcut tricks is just break this to double bond and attach oxygen with this carbon center, then you can get the product. For example, if we take this molecule CH3 CH double bond CH and CH2 CH3, then if we use here ozone first at the first step, then first it will form a 3-member cyclic transition state like this: CH3 CH CH CH2 CH3, then a 3-member cyclic transition state will form here. And if you use here zinc and water, then it will rearrange, and after rearrangement this bond will break, and after rearrangement it will form CH3 CH double bond O here, and another one is H bond C double bond O, CH2 and CH3. So this is the product, the final product. So how can you get this final product? By just 20 seconds. So just break down these two bonds and use oxygen just like this: CH3 CHO here, and another one is CH3 CH2 and here CHO. Then you can get the final product just only 20 seconds. So this is the tricks to form ozone lysis reactions. For example, if you take this double bond, this is a cyclohexene, and if you use here first ozone and then zinc and water, then after reaction you will get this product only. Just break down these two bonds and attach oxygen with this carbon atom. Just the product it will be this one. So just write down this product in linear form. It is 1, 2, 3, 4, 5 and 6 carbon atom is present. So 1, 2, 3, 4, 5 and 6. So they are present another carbon atom. So the final product it will be this. And if you follow the mechanism, then first it will form a ozonide product, just looks like this. This is the ozonide product, and then this bond, if you use zinc and water here, then this ozonide will break like this way, and the final product it will be this one: double bond O, double bond O, here present one hydrogen and here present another hydrogen. So the product it will be same, but it is the actual mechanism path, but this one is the tricks by which you can get the product only. So this is the ozone lysis reaction. Again, if I take another examples, like if I take these molecules and if you use here ozone and zinc H2O, then the product it will be very easy. Just break down these two bonds and the product it will be this one. First one is this and the next one it will be this. So this is the final product. So this is the ozonolysis reaction. And one thing, if you use benzene as a reactant, and if you use their ozone and zinc H2O, then after reaction you can get 3 molecules of glyoxal, that is CHO and CHO. So this is the reactions. And how can we get this? You have to break down this 3 bond, and after breakdown you can get this product. There present one oxygen atom, another oxygen atom here, and from the other part you can get this molecule, and from the other part you can get this molecule. So after reaction you can get 3 molecules of butyl DNA. So this is the ozonolysis reactions of double bond. Next one is oxidation of double bond in presence of potassium permanganate. Oxidation of double bond in presence of potassium permanganate. So what is the structure of potassium permanganate? You know about that. There present manganese in the center, oxygen, double bond O, and here present O minus K plus. This is the structure of potassium permanganate. And if you use this aqueous solution of potassium permanganate with the double bond, for example this one is the unsymmetrical double bond, and if you use potassium permanganate here or aqueous solution of potassium permanganate, then you can get the diol product or C1,2 diol product type. That means CH, there present OH, and CH2, there you have to attach another OH1. This is the diol product, or you can say vicinal diol product. So in terms of aqueous KMnO4, this double bond oxidized to vicinal diol. So what is the mechanism? It follows very simple mechanism, just like this. R CH double bond CH2, they present potassium permanganate, and it will follow just but looks like butterfly mechanism. Just it attached here, this double bond will attached here, and this is the cyclic 6-member transition state. It will follow. Sorry, it's not 6-member, it is a 5-member cyclic transition state, and after that it will form this molecule. This is a manganese, and 2 double bond will attached here. And after hydrolysis, this molecule, hydrolysis means in presence of water, this two bond will break and it form OH. So the final product is R CH CH2, one OH here and another OH here. That means the vicinal diol product, it will form vicinal diol. So simple reactions, if you add aqueous potassium permanganate with double bond, any type of double bond, for example it is a cyclohexane again, and you use KMnO4 and water, then the product it will be diol. And one thing, if you notice the mechanism, the OH will attach with the double bond with the same side. So you can say it's a cis OH. It's a cis product. Always remember this. So when you use potassium permanganate with double bond, then it will form always a cis product. And this reaction also used to identify the double bond. You know the potassium permanganate, the color of potassium permanganate, it is violet. So if you prepare a very dilute solution of potassium permanganate and drop-wise added this potassium permanganate solution to the double bond product or alkene product, then after reaction the violet color of the potassium permanganate will disappear. So this is an identification test of double bond also. This reaction also used for the identification of double bond. Same type of reagent, another reagent is osmium tetraoxide. If we use osmium tetraoxide with double bond or alkene, then same reaction, same type of reactions is going on, and you can get same product, that means OH, and here CH2OH, that means vicinal diol product you can get. So again it is oxidation of double bond by using potassium permanganate or osmium tetroxide. Next one is bromination of double bond. Bromination means if you take alkene and if you use bromine and CCl4, or you can use water also, bromine water or bromine CCl4, then the product it will be CH, one bromine will attached here and one bromine will attached here. This is the bromination of double bond, and this reaction also used to identify the double bond because it is a bromine water test, you know. Bromine water or bromine CCl4 both you can use. So just first you have to prepare the dilute solution of bromine, and same like potassium permanganate solution, you have to add drop wise this bromine water with the alkene, and then you can see the yellow color of the bromine. This the color of the bromine, it is yellow. The yellow or brown, yellowish brown color of the bromine, it will disappear when you add this bromine water with this double bond. But remember, you have to use very dilute solution of bromine. If you use concentrated solution, then sometimes it show problem. So you have to use very dilute solution of bromine. Then just when this bromine water touch this alkene solution, then you can see the color of the yellow color of the bromine, it will disappear. So it is also an identification test of double bond. Same, any type of double bond, if you take any type of double bond, for example this one, another molecule, and if you use here bromine and water or bromine CCl4, then the product it will be 2 bromine will attached here. That means addition of bromine to the double bond. Just a simple reactions. Any type of double bond you can take. Just after adding of this bromine, you can see the di, or again you can say the vicinal dibromo compound. So if we take this molecule again, and if you use here bromine and CCl4, then the product it will be 2 bromine will attached here. So this is the bromine addition with double bond. Similarly, one thing you have to remember, it is a benzene. If you use here Cl2 and normal sunlight, then what will happen? All double bond will break, and first you have to use 6 chlorine atom, then all carbons or all double bond now break down and it forms hexachlorobenzene. Okay, so this is another reactions. So this is the addition of halogen to the double bond.